Welcome back, everybody. Today we're going to finally start talking about modular curves as curves over the rationals and not just over the complex numbers. To do that, we're going to have to consider the Galois action on torsion of the universal elliptic curve over Q, or more specifically over Q adjoin J. How does the theory from the previous video, and if you haven't watched that yet, please do so now, change when I change the underlying field from the complex numbers to the rational numbers? That's the underlying question of today's video. We'll set up the groundwork for that. Note that the universal elliptic curve E sub j has coefficients not just in C adjoin j, but in Q adjoin j, if you go back to the previous video and see the formula for it. Now, viewing this elliptic curve E sub j as an elliptic curve over Q adjoin j means I'm inherently concerned with solutions in the algebraic closure of Q adjoin j. When I study an elliptic curve over a field, I'm concerned with its solutions in the algebraic closure of that field. Now, these points include the non-zero points of the end torsion of the universal elliptic curve, because those are solutions to polynomials whose coefficients are functions of the coefficients of the elliptic curve, which live in Q adjoin j. Okay, so let's let H sub Q be the Galois group of Q adjoin the nth roots of unity, the j invariant, and the end torsion of the universal elliptic curve E sub j over Q adjoin j. And let me consider the representation rho from HQ to GL2 of Z mod NZ, given by the action of Galois on the end torsion of E sub j. Remember, actions of groups on sets are the same thing as representations. Okay, so like what's going on here is n torsion of E sub j is as a group abstractly isomorphic to Z mod NZ squared. Okay, and so I'm going to get a representation, two-dimensional representation from HQ to GL2 of Z mod NZ, because Z mod NZ squared is basically exactly as a group E sub j, the n torsion of E sub j. Okay, so if I pick an ordered Z mod NZ basis P tau Q tau of the n torsion of EJ, it's easy to check that sigma of P tau, sigma of Q tau, so the vector whose coordinates are sigma of P tau, sigma of Q tau, that's just the same as a rho of sigma times the vector P sub tau, Q sub tau for all sigma in the Galois group H sub Q. In other words, the Galois action can be considered coordinate-wise on vectors. That's what's going on here. Okay, so also more importantly, maybe though, or at least as importantly, I should say, det rho, the determinant of this representation here, this governs how Galois permutes the nth roots of unity. What I mean by that is, it turns out sigma of mu is the same thing as mu to the det rho power for all nth roots of unity mu and for all sigma in the Galois group. And this is actually shown via the Weil pairing, which is why I made a video on the Weil pairing. Okay, now let's suppose I have sigma in the Galois group fixing n torsion of EJ. Then by definition, sigma is in kernel of rho, so sigma is in the kernel of det rho. Okay, but then this fact up here tells me that sigma must fix mu n, right? Because if it's in the kernel of det rho, then det rho is 1. And so I'll have sigma of mu is just mu for all mu and mu n. Okay, and so in other words, the nth roots of unity are fixed by sigma. And then Galois theory tells me, all right, well then mu sub n is just in Q adjoin j and the n torsion of E sub j. All right, so if I fix n torsion of EJ, I automatically fix mu sub n. So mu sub n has to live in this extension whose Galois group I'm considering, right? That's just basic Galois theory. This tells me that HQ is in fact just the Galois group of Q adjoin j and the n torsion of E sub j over Q adjoin j. So that's why I sort of initially, it looked like I was artificially adjoining mu sub n here. No, the point was you adjoin mu sub n and then you show it's already here. It's already in this field to begin with still. Okay. Now, because of this fact, I can construct the following diagram of Galois groups. So I've got now kind of three interesting fields. I've got Q adjoin j, the base field. I can tack onto that mu sub n. And then I can also tack onto the base field just the n torsion of E sub j, because I know by the above that mu sub n already lives in this field. So that breaks down my Galois group H sub Q into kind of two pieces. I've got the Galois group of this first extension here, Q adjoin j and the n torsion of E sub j, over Q adjoin mu sub n and j. I'll call that Galois group H sub Q adjoin mu sub n. And then, of course, from basic algebraic number theory, I have the Galois group of Q adjoin mu sub n j over Q adjoin j. That's just going to be Z mod NZ star. Okay, and then I've got my representation rho from HQ to GL2 of Z mod NZ. It turns out that because Q adjoin j and the n torsion of E sub j already contains mu sub n by the above, rho is injective. It's easy to see that now. That follows from the description of its action on n torsion. So what's going on here is, if rho of sigma is trivial, then it's trivial on n torsion by this fact. Okay, but then we already know it's automatically trivial on roots of unity by this fact. So it's trivial on everything. So it's the trivial automorphism. Okay. So if in other words, if sigma is in the kernel of rho, then it's the identity, right? So this is an injective representation, right? Now, you can also see not only is rho injective, but you might ask, well, what does rho look like when restricted to this Galois group, for example? Like, where's the image? Well, because of the relationship between det rho and the action of HQ on nth roots of unity, rho restricts to a representation from H sub Q adjoin mu sub n to SL2 of Z mod NZ. And the reason for that is when I restrict down to this subgroup of the Galois group HQ, I'm fixing mu sub n, you see. If I'm fixing mu sub n, my determinant's 1 by this fact here. So my image won't just land generically in GL2 of Z mod NZ, it'll land in SL2 of Z mod NZ, determinant 1 matrices. Okay, so important theorem of the day. I need to, in order to discuss modular curves over Q, I have to know how to detect function fields of Q curves. Using the restriction lemma from Galois theory, the above discussion, and a little bit of work, we arrive at the following algebraic analog of certain results over C that were discussed last video. I'll call this theorem 2. So let's let H sub Q be the big Galois group as discussed above. So it's the Galois group of Q adjoin J, and n torsion of E sub J over Q adjoin J. It turns out there's an isomorphism rho from HQ to GL2 of Z mod NZ. It's not just injective rho, it's an isomorphism, okay? And furthermore, if I let bold K be an intermediate field of the extension I'm concerned with, Q adjoin J, n torsion of E sub J over Q adjoin J, with corresponding subgroup K in the Galois group, remember intermediate fields of this extension correspond to subgroups of the Galois group by basic Galois theory, then bold K intersect Q bar is Q if and only if det rho viewed as a function of K surge X onto Z mod NZ cross. Okay, so if you go back to the definition of function field I gave several videos ago, what this is saying is that bold K here, any intermediate field extension of Q adjoin J underneath Q adjoin J and the n torsion of E sub J, that's going to be a function field of an algebraic Q curve if and only if det rho surge X on J. Okay, and this last statement, by the way, follows from the curve's fields correspondence, of course. And so I'm going to be concerned primarily with extensions of Q sub J living underneath this torsion extension here that satisfy this property here.